Hello everyone. Today we are going to solve the governing differential equation of your simply supported beam that is subjected to uniformly distributed load. But before we get straight into the business of solving the governing differential equation of your simply supported beam that is subjected to uniformly distributed load, I would like to tell you the goal of finite element analysis. Remind yourself that the goal of finite element analysis is to make sure that the stresses are within the acceptable limits for all types of materials chosen and for all types of environmental conditions encountered. So if you are going to be an engineer, you have to make sure that the structures that you build or the mission components that you design, you have to make sure that the stresses are within the acceptable limits. So that is the goal of strength of materials. That is the goal of finite element analysis, particularly if you are defining the goal through the lens of mechanical engineers. So that is the goal. So our objective here, of course, in this particular problem, our objective here is to find the values of stresses. Now if you solve the governing differential equation, I will write the governing differential equation for you. It is EI d raised to the power 4 v by dx raised to the power 4 minus q naught is equal to 0. So this is the governing differential equation that we derived in the previous video. Sometimes they use plus sign, sometimes they use minus sign. Whether you want to use a plus sign or minus sign, if you want to get the value of deflection in negative, because the deflection is going to take place most probably in the downward direction, you may want to flip the sign, but it is by convention, so it's not a big deal. So this is the governing differential equation that we derived in the previous video. Now what is that you will be getting if you solve this governing differential equation? You will not be getting the values of stresses right away. If you solve this governing differential equation, you are actually going to get the value of deflection, V. Deflection is denoted by the symbol V. Now, if you know the value of deflection, there is a relationship between deflection and bending moment. So you can actually get to the value of bending moment if you know the value of deflection. And if you know what is the value of bending moment, you can tell what is the value of bending stress. You can tell the value of bending stress. So you see, that is the goal. Finally, you are going to compute the value of bending stress. In a similar note, if you know the value of deflection, you can actually find the value of the shear force. And if you know the value of shear force, you can tell what is the value of the shear stress. Shear stress is denoted by the notation tau. So you see, by solving the governing differential equation, you can squeeze out all these values. Okay, now let us solve this governing differential equation. But there is one more thing that you have to define before you solve this governing differential equation. What is that? Well, you have to define the boundary conditions. What is the boundary condition? Quite axiomatic. It is quite straightforward. The boundary conditions are quite straightforward. It is a simply supported beam. So what about the deflections on the left hand side or the left extreme end? And what about the deflection on the right extreme end? There is not going to be any deflection. Well, so therefore the deflection at the left extreme end is going to be 0. And the deflection at the right extreme end, V of L is equal to 0. So the deflection at the point x is equal to 0 is going to be 0. And the deflection at the point x is equal to L is going to be 0, where x being reckoned in this direction. That is the first set of boundary conditions. Maybe you may want to call this as the first boundary condition. You can call this as second boundary condition. What about the third boundary condition? The bending moment. If you draw the bending moment diagram of a simply supported beam that is subjected to uniformly distributed load, the bending moment diagram would look something like this. I'll just draw the bending moment diagram for you. We don't have the luxury of time to draw the bending moment diagram. We have to take my word for it. The value of bending moment at the left extreme end is actually 0. The value of bending moment at the right extreme end is going to be 0. So that gives us the second set of boundary conditions. So you say the second set of boundary condition is bending moment denoted by the symbol M. You know what is bending moment? What is the expression for bending moment? The expression for bending moment is EI into d square V by dx square. At the point x is equal to 0 is going to be 0. This is the expression for bending moment. If you are wondering how we get this particular expression for bending moment, please go back and watch the previous video. In the previous video, this particular expression for bending moment, we have derived this particular expression. So please remember the expression for bending moment is EI into d square V by dx square. You have to burn this particular expression into your brain. It is very, very important. So the bending moment at the left extreme end is going to be 0, and the value of bending moment at the right extreme end is going to be 0. So EI into d square V divided by dx square at x is equal to L, which means that the right extreme end is going to be 0. So before you solve the governing differential equation for this particular physical scenario, you have to define the boundary conditions. I think we have clearly defined the boundary conditions. The value of bending moment at the left extreme end is 0. The value of bending moment at the right extreme end is 0. The value of deflections at the left and right extreme ends is 0. Okay, now we will solve the differential equation. I think you know the procedures. You should be conversant with the procedures now. So we know the procedures. What is the first step? I will just tell you the steps. The first step, it is to assume a trial solution. That is the first step. If you look back at the previous problems, we would have followed a series of logical constructive steps in order to arrive at the solution. So I will just race through the steps, then we will do the steps one by one. So the first step, it is to assume the trial solution. First step is to assume a trial solution. So what is the trial solution that you are going to assume? What is trial solution? What is the trial solution that you are going to assume? Well, if you plot the value of deflection of the beam and you take it along the y-axis, and if you plot the value of x, which is arbitrary distance from the left extreme end, you are going to get a deflections curve something like this. Because the deflection at the left extreme end is going to be 0, the deflection at the right extreme end is going to be 0. Since this is a beam that is subjected to uniformly distributed load, the loading is perfectly symmetrical. The deflection at the center, which is at x is equal to L by 2, that is going to be maximum. So the deflection spikes at the center. Our objective here is to find this particular equation. If you know this equation, you can tell what is the value of deflection without having to measure the value of deflection practically. So you see there is a tremendous economic utility in finding the values of deflection by solving the differential equation. So how do you predict this particular equation? Well, that is very simple. All you have to do is localize your attention on this governing differential equation. Just localize your attention on this governing differential equation. All you have to do is you have to integrate this particular governing differential equation 4 times. If you integrate this governing differential equation 4 times, you will be left out with an equation for V, which is going to be a polynomial equation. So if you differentiate it 4 times, you will be left out with a polynomial equation. And what would be the order of the polynomial equation? The order of the polynomial equation is going to be 4, because 1 time integration is going to give you the value as q naught x plus some constant. 2 times difference integration, that is going to give you the value as q naught x squared by 2. 3 times integration, it is x cubed. 4 times integration, it is x raised to the power 4. So it is quite obvious that the order of the governing differential equation is going to be, the order of the polynomial equation is going to be 4. So that is one way to define the trial solution. So I will say that the trial solution is V of x is equal to a naught plus a1x plus a2x square plus a3x raised to the power 3 plus a4x raised to the power 4. So this is the trial solution. Now if you still wonder how we get this trial solution, please go and watch the second video. I have clearly explained, I think I have given explicit instruction on how we actually arrive at this trial solution. So all you have to do is integrate the governing differential equation 4 times. But here is the surprise for you. You can perfectly solve this problem by assuming this trial solution. But see, I have got a surprise for you. What I'm going to do is I'm going to erase this. So I am erasing this, which means that I am not going to assume this trial solution. Now why is that I will not assume this trial solution? I'm going to assume another trial solution, and you will appreciate the trial solution that I assume. The trial solution that I am going to assume is v of x. This is a surprise for you, maybe a mystery for you. It is a into sine pi x over L. Maybe it is a surprise. For some of you, it may not be a surprise, but there is a perfect logical reason, and you will appreciate why I have assumed this particular trial solution. The reason why I have assumed this particular trial solution is this trial solution immediately satisfies the essential boundary conditions. It immediately satisfies all the boundary conditions. So let us go back and watch our boundary conditions. Let us revisit our boundary conditions. The first boundary condition is the deflection at the left extreme end is going to be 0. This is the first boundary condition. Deflection at the left extreme end is going to be 0. And the deflection on the right extreme end is going to be 0. You see that if you put x is equal to 0, the value of deflection is 0. So I will write the second step for you. The second step is when you apply the boundary conditions. So I will write that. Apply the boundary conditions. At x is equal to 0, if you substitute the value of x as 0 here in this equation, what is going to happen to the value of deflection? In this equation, a into sine pi into x becomes 0, so it becomes 0. So this boundary condition is readily satisfied. So I'm putting a tick mark here. So that is a tick mark. You have to believe that is a tick mark. Okay. What about the next boundary condition? At x is equal to L. What happens when you substitute the value as x is equal to L? What is going to happen to the value of deflection? If you assume this trigonometric trial solution, it is a into sine pi into L over L. So L, they cancel each other out. Sine 180 degree, what is the value? It is going to be 0. So that boundary condition is also satisfied. Let us look at the third boundary condition. What is the third boundary condition? Third boundary condition is bending moment, which is EI into d square v by dx square. What about that boundary condition? Well, you look at the trial solution, you differentiate it 2 times, find the value of EI into d square v by dx square. What is going to happen? If you differentiate it 2 times, 1 time differentiation is going to give you the value as cos pi x over L into pi by L. 2 times differentiation is going to give you the value as minus sine pi squared by L squared into sine pi x over L. So I'll write that here. So 2 times differentiation, it is EI into pi square over L square into sine pi x over L. I think I'm missing a negative sign here, so I'll put a negative sign. So this is EI into d squared v by dx squared. What happens when you put x as 0 in this equation? So when you put x as 0 in this equation, this term is going to give you the value as 0. What happens when you put x is equal to L? When you put x is equal to L, again it becomes sine 180 degree. So again this term is going to become 0. So the value of bending moment at the left extreme end is going to become 0. The value of bending moment at the right extreme end is going to be 0. So you see that the boundary conditions are readily satisfied. Okay, now what is that is the end of step number 2. So we have done 2 steps. First step, we have assumed a trial solution, so I'm putting a tick mark for that. I think you're fine with that. The second step, applying the boundary conditions, I'm putting a tick mark for that. I think you are fine with that. The third step, what is the third step? The third step is to find the value of d raised to the power 4 v by dx raised to the power 4. Now, why do you want to find d power 4 v by dx power 4? Why do you want to find that? Because that is exactly what is demanded in the governing differential equation. You look at the governing differential equation. I'll indicate that here. Look at the governing differential equation. What is demanded in the governing differential equation is d power 4v by dx power 4. So if you know the value of d power 4v by dx power 4, you can put it right here, and you can turn the crank of mathematics and see whether you can find the value of the constant. So find d power 4v by dx power 4. So what is going to be d power 4v by dx raised to the power 4? What is that you will be getting? You will be getting the value as a pi raised to the power 4 over L raised to the power 4 into sine pi x over L. I invite you to do this differentiation and check it. You'll be getting a pi raised to the power 4 divided by L to the power 4 into sine pi x over L. So that is the value of d power 4v by dx power 4. All you have to do is take this value and substitute it in the governing differential equation. I will write that governing differential equation is ei d power 4v by dx raised to the power 4 minus q naught is equal to 0. I'm sorry about this terrible handwriting. Anyway, take this value and put it here. Put it here. So I'll do it in the next step so that we can find the value of the constant. Once you know the value of a, small a that I have written here, everything is over. Everything is going to be over. So let me do the next step. So I'm going to substitute step number 4. I'm going to substitute the value of d raised to the power 4 v by dx raised to the power 4 in the governing differential equation. So what is that you will be getting? You will be getting ei into, what is d power 4 v by dx power 4? It is a into pi raised to the power 4 divided by L raised to the power 4 into sine pi x over L minus q naught is equal to 0. But there is a big problem. If you look at this mathematics is staring at us, and there is a very big problem that we are facing actually. If you can find out what is that problem, maybe if you just delve deeper into this particular equation, this equation is posing us a big problem. What is that big problem? There is a mathematical violation that we are facing. This equation poses a threat. That threat is mathematical violation. What is this mathematical violation? What is this mathematical violation that we are facing? That mathematical violation is, if you turn the crank of mathematics and if you try to find the value of a, all you have to do is you have to throw every term on the right hand side. You'll be taking every term on the right hand side. Take this term on the right hand side, take this q naught on the right hand side, take this sine pi x over L on the right hand side, take this ei onto the right hand side. The problem if you take them on the right hand side is, if you take this sine pi x over L on the right hand side, you will be finding the value of a in terms of, I will write that here, in terms of sine pi x over L. So you may ask me this question, so why that should be a problem? That is a serious mathematical violation because A is a constant. If it is a constant, it should not change with respect to time. Whereas if A should not change with respect to time, if you look at the right hand side, x is a variable. It represents an arbitrary distance. X is a variable. X represents the distance, a distance at x is equal to L by 2, which means when x is equal to L by 2, you are localizing your attention at the center of the beam. When x is equal to capital L, you are localizing your attention on the right extreme end. If x is equal to L by 3, x is equal to L by 4, which means that x represents any arbitrary position on the beam. So definitely it is not a constant. It is not a constant. It is a variable where A is a constant. So what do you do? What do you do in order to alleviate this problem? If you cannot say that the right hand side is going to be 0. This is wrong. So I will rewrite this equation. So let me rewrite this equation because the right hand side definitely it cannot be 0. If it is, definitely it cannot be 0. There is a serious mathematical violation because you are finding A in terms of a constant in terms of a variable. So let me do the next step. So what you have to do is, I'm rewriting that expression. It is EI d raised to the power 4 V by dx raised to the power 4 minus q naught is equal to 0. Of course it is 0, that is what the governing differential equation is saying. But once I substitute EI into d power 4V by dx power 4 is A into pi raised to the power 4 over L raised to the power 4 into sine pi x over L minus q naught. Definitely it is not 0. If you put 0, you will be finding the constant in terms of a variable. So there is an error in this equation. That error, you can call this error, where R here stands for residual. There is a residual error. We will see the physical meaning of this residual error. Definitely we are going to look at the physical meaning of this residual error. When we delve deeper into the subject matter, we will understand what is the physical meaning of this residual error. Okay. You can avoid this problem only when you make this x, which is a variable, you have to make it a constant. You have to make it a constant. So how do you make this variable x a constant? Well, you have to put your value for x. So what is the value for x that you are going to put? Well, it is at your discretion. It is at your volition. You can put the value of x as L by 2, which means you are talking about the center of the beam. Which means you are talking about the center of the beam. You can put the value of x as L over 3, which means you will be talking about this particular position. Let us say that it is at a distance of L over 3. So x is an arbitrary distance. So let me make the residual 0 by fixing the value of x. Let me put x is equal to L over 2 and let me find the value of the constant. Once I have got the value of the constant, then the problem is over. So put x is equal to L over 2 in this particular equation and for residual, and let me see what is the value of constant that I am getting. So if I put x is equal to L over 2, the equation that I will be getting is EI into A into pi raised to the power 4 over L raised to the power 4 into sine pi x is L over 2, so it is L over 2 pi x by L minus q naught is equal to 0. So I am making the value of residual 0 at x is equal to L over 2. Remember, residual is analogous to error. You have to burn that into your brain. So just to find out the value of the constant a now, a is equal to q naught. Take this q naught to the right hand side and take this L power 4 to the right hand side. It becomes L raised to the power 4. It goes to the numerator and everything else goes to the denominator. EI goes to the denominator. Pi raised to the power 4 goes to the denominator. This term, it just becomes 1 because sine 90 degree, it just becomes 1. So that is the value of the constant q naught into L raised to the power 4 divided by EI into pi raised to the power 4. Next comes, once you have got the value of the constant, all you have to do is substitute the value of the constant in the trial solution. So that is the last step. All I have to do is substitute the value of the constant in the trial solution. The trial solution is a sine pi x over L. This was our first step. All I have to do is substitute the value of the constant. So it becomes q naught L raised to the power 4 divided by EI pi raised to the power 4. That is the value of a into sine pi x over L. So that is the solution to our problem. So this is the solution. Now if you ask me this question, how accurate this solution is, the accuracy is not going to be that great. Let me tell you the reason why it is not going to be that great. The reason is you are making the residual, which is analogous to error, 0. You made the error 0 at x is equal to L over 2. You can also make the residual 0 at x is equal to L over 3. If you are making the error 0 at x is equal to L by 2, then at all other points, error should be there. So at all other points, error just kicks around. This is very important. So you are making the error 0 only at chosen points. This process of making the error 0 at only chosen points is what is called as point collocation method. This process of making the error 0 at chosen points is what is called as point collocation method. Now, let us interpret this residual. We don't want the error to be 0 only at selected points, which means that if you are making the error 0 at x is equal to L by 2, only at x is equal to L by 2 you will be getting the exact solution. If you are making the error 0 at x is equal to L by 3, only at x is equal to L by 3 you will be getting the exact solution. If you are making the error 0 at x is equal to L by 4, only at x is equal to L by 4 you will be getting the exact solution. Okay, there is still more to it. Let me explain you that. Okay, the equation for residual. If you look at the equation for residual, so I'll just project the equation for residual here. This is the equation for residual, this one here. Now let me write that equation. It is EI into A into pi raised to the power 4 divided by L raised to the power 4 into sine pi x over L minus q naught. So that is the equation for residual. Now at x is equal to L by 2, as far as our previous problem is concerned, R is 0. At other points R exists. So I can plot a graph. By taking the residual along the y-axis and x along the horizontal line. Now what is the type of graph that you are going to get? Well, if you plot this particular graph, you will know that this R should become 0 at this point. At x is equal to L over 2, the value of R should go to 0. That is the meaning. But at other points, so let me draw a graph very roughly here. So this is a rough sketch. This is not going to be an actual plot. We will do the actual plot, but let me say that roughly, if you plot a graph, you see the value of error becomes 0 only at x is equal to L over 2. But at other points, you see, let me shade this region. It indicates error. This region indicates the error. So our objective, you see, our objective is to make the error 0 not only at this particular point. Our objective is to make the error 0 not only at this particular point, but we want to reduce the error in an overall sense. So how can you make the error 0 in an overall sense? Well, all you have to do is make this area 0. Make this area 0. Maybe you may want to make the error area 0. So if you're getting a graph, something, so let me do that. It is again a rough sketch. If you're making the residual area, let me say that the residual varies something like this. If you are making the residual, if you want to, so our objective here is to make the value of error 0 in an overall sense by making the area 0. Now I will again plot this graph by taking the residual along the y-axis. This is a random graph. This is a completely random graph. By taking the residual along the y-axis, I'm just plotting a random graph here. So this is a completely random graph. The way you make the residual area 0 is, if you want to find the area beneath this error curve, the y-axis, the height of this triangle is going to be r, the length is dx, because r is being plotted along the y-axis and x being plotted along the x-axis. If you want to find the area of this curve, all you have to do is, area of the small strip is r into dx. Now how do you find the total area? Well, it is, you have to integrate it over the limit 0 to L. And if you can make this area 0, what does it mean? If you are making this area 0, it means that, if you make this expression 0, it means that you are making the error area 0. So that is a very important point. You are making the value of, if you are making the error area 0, which means you are sort of making this curve come down. You are sort of making this curve come down so that you try to iron out the wrinkles and make this curve as low as possible so that the area becomes 0. That method, this method, should be superior to point collocation method, because in point collocation method you are making the error 0 only at chosen points. But you see, in this method you are making the error 0 in an overall sense by making the area of the error curve 0. And this method, where you make the area 0, is called as subdomain collocation method. So before we get into subdomain collocation method, you may fancy a short break, but I have to tell you that we have to physically interpret, the physical meaning of residual. So still, what is this residual? I will give you a clue and you can think about it. What is this residual? So here is the equation for residual. So let me project that equation for residual here. Here is the equation for residual. Now in this particular equation, maybe I will take a fresh page and I will write that equation for you. So here we go. I'll just take a fresh page. Here we go. The equation for residual is r is equal to ei into a into pi raised to the power 4 over L to the power 4 into sine pi x over L minus q naught. So that is the residual. What is the physical meaning of this residual? What is the unit here? Q here is Newton per meter. If this is Newton per meter, then this unit should also be Newton per meter, so that you can add or subtract these two. If these two are in Newton per meter, then the residual should be in Newton per meter, which means that, I'm just giving you a clue, a residual has its unit as Newton per meter, which means it is analogous to rate of loading. It is something that is similar to rate of loading. So which means that at x is equal to, let me give one example. This is a simply supported beam that is subjected to uniformly distributed load. At x is equal to L over 3, let me give one example here. Let me say that the error value is, let me say that it is 10. If the value of error is 10, I will use a different color here, different notation. If the value of error is 10 right at this point, it means right at this point, the rate of loading is of the error of 10 Newton per meter, which means if the rate of loading is, let us say, if it is 2 Newtons per meter, then maybe the rate of loading is 12 Newton per meter at the point x is equal to L by 3. This is just an example. Of course, the values are completely erratic, but just an example to get across the concept. So that is the meaning of the residual. So the meaning is, you have to wrap your mind around the physical meaning of the residual. You see, at x is equal to L by 3, the error is 10. If the value of the residual is 10, it means that 10 Newtons per meter, it means that at x is equal to L by 3, the rate of loading has an error of 10 Newton per meter, which means that on top of already existing 2 Newtons per meter, there is an additional 10 Newton per meter, which is completely superfluous, which is completely unnecessary, that is acting at x is equal to L by 3. That is the meaning of the residual. So you see, when you put x is equal to L by 3, L by 2, and you make the residual 0, at x is equal to L by 2, the value of rate of loading at x is equal to L by 2, which is at this point, it is just 2. The actual rate of loading is acting. So that is fine. But at other points, the rate of loading, there is an error. And the error is 10 Newton per meter, because on top of 2 Newton per meter, there is an additional 10 is acting. So that becomes 12 Newton per meter. That is an error. So it gives a solution to the problem. It gives a solution as if the rate of loading is 12 Newton per meter. So the solution that you will be getting will be the solution for 12 Newton per meter, not for 2 Newton per meter. However, the rate of loading becomes 2 Newton per meter at x is equal to L by 2. So that is the physical meaning. So that is the physical meaning of the residual. So give it some time for the concepts to sink in. The next method is going to be subdomain collocation method. We will delve deeper into the subject matter. Thank you for your time. Thank you.